Swayam Prabha. Digital India. Educated India.
Hello, good morning. So, welcome to the today's class on comprehensive view of speech processing, and today's lecture is lecture number 24 in the series, and today we are going to discuss about the vector quantization. So, before going to the today's topic, so far in the last lectures, about 4 to 5 lectures, we discussed about the features, how do we extract the features from a speech signal. So, from that viewpoint we discussed about various types of features, that is features that can be extracted from a time domain and features that can be extracted from a frequency domain, right. And in case of time domain we have looked at the features like a short term energy envelope, and then zero crossing rate, autocorrelation, then average magnitude difference function. So, these are some of the features we can directly extract from a time domain representation of a speech signal, and that can be useful for for performing various speech tasks like voice unvoiced decision and identifying the boundaries of sound units, and some indirect way of giving a spectral information and computing a periodicity, the pitch and so on. So, these are the various ways we can use the features that can be extracted from a time domain representation. And there are other way that it's for sometimes it's better to look at the features in a spectral domain. So, in that context we analyze the age old technique known to be filter bank analysis. So, passing the speech signal, the wideband speech signal, through a set of narrowband filters, and where each filter output energy will be tapped, and then all these energies from the outcome of the filter bank can be viewed as a feature vector, and that can be utilized for different speech tasks. And we also seen that the filter bank analysis can also be used for speech coding purpose. It means that the compact representation of a speech it can be used for speech transmission, basically targeted for speech code, speech transmission, or basically the telephonic applications where it is mainly targeted for. So, that we discussed in the context of filter bank analysis. So, initially the filter bank analysis is very extensively used for telephonic application for speech transmission. It means how do we can represent the speech in a very compact way, so that we can utilize the very less bandwidth, and so that the channel efficiency can be increased. So, those are the applications that are targeted at initial point of a time till 70s also, and after that, due to the increase in computational power, availability of these computational resources and all, the other speech tasks also gain the popularity, like speech recognition, speaker verification, authentication, and language identification and so on. So, therefore, the filter bank analysis is first very much limited or targeted for speech coding. Later it can be used for the other applications like speech recognition and so on. Then after that we covered the linear prediction analysis of a speech, where like by using a source filter concept of a speech production, that means the speech is produced by a convolution of excitation signal with the vocal tract response. So, then based on that we assume that the speech is the speech signal is a correlated one. That means the samples that are present in the speech signal are highly correlated, because it is produced by the physical system, human speech production system, where the articulators have the limited movements, and with that the signal that was emitted from the oral cavity or a nasal cavity will be like highly correlated. So, since the signal is contains the higher amount of correlations, so we can able to predict the samples from the preceding history, or by knowing the previous samples and all. So, that way the linear prediction analysis or linear prediction model can be applied for a speech production system. With that we can able to parameterize the speech in terms of the prediction coefficients, and by using the prediction coefficients we can also analyze the error signal, and that in turn the error signal can be viewed as the excitation, so that the desired speech can be generated from the signal. So, we analyze the speech both as the this one, the synthesis model, and as well as the analysis model also. In the context, by using analysis model, we can able to compute the linear prediction coefficients. Then by applying the linear prediction coefficients, then we can able to synthesize the speech also. So that way the linear prediction coefficients are also can be viewed as the features or the representation of a speech for the applications like for synthesis purpose and so on. But the linear prediction coefficients are very sensitive. So therefore, if you want to use the linear prediction coefficients or a knowledge from the LP spectrum, if you want to use it for various speech tasks, so we need to use its capsule representation, right. So the linear prediction capsule coefficients, the computation process of that. So all those things we have discussed in the last class, and today because of the limitation of time, so we are not able to cover the other feature extraction techniques. There are other existing feature extraction techniques which due to limitation of time we are unable to cover that, like for example harmonic plus noise model, right, and then the group delay analysis of a speech, sinusoidal modeling of a speech. So there are various types, various ways we can able to like analyze the speech signal and capture the appropriate features and all. And so those who are interested, they can able to go through these corresponding methodologies for extracting different types of features as I have mentioned and all. And now we move on to the next topic, that is vector quantization. And here in this vector quantization, so this can be used for one way is that this can, by using a vector quantization, we can we can able to derive the features, and we can also represent the speech also in a very compact way, and we can also perform certain speech tasks using the vector quantization directly, right. And we have seen, before going to the details, we know that we already come across the terminology like quantization when we are capturing, when you are in the process of acquisition of a speech signal through microphone and afterwards converting the continuous speech signal to the digital, where we come across the stage or module known to be quantization. So it's nothing but approximating the actual amplitude to a known level or to known reference the value and all. Because of a finite precision offered by the computers and all, we cannot represent the actual amplitude, because it's a real quantity, and then you cannot by using a finite precision you cannot represent that. So therefore we need the quantization. So we discussed about the quantization in that context when you are digitizing the speech signal and all. And that quantization can be viewed as a scalar quantization. That means we have some value and we will try to quantize that to the nearest known level or known value and all, approximate value. And in that process, we already know that since we are approximating that, instead of representing the actual value to by its nearest value, so therefore there will be some error will be bounded, will be occurred in that, and that error is known to be quantization error. And it's a scalar quantization. That means we have some value, and for representing that value, since this value is a real value and with a finite precision you cannot represent on emissions, so therefore we will try to represent with some finite precision using some available finite number of levels or finite number of values and all. So that process is known to be quantization, and that's a scalar quantization. That means we are just representing the value, one value, we are rounding off the value to the nearest value, whereas here it's a scalar quantization. And now here in this topic we will try to discuss about the vector quantization. So vector quantization means, we know that all of us are aware of that, what is mean by vector, right. So the vector means actually here it consists of multiple values, and then all those values happens to be a components of a vector and all. Suppose for example in the spectral analysis what we have seen, for example in case of filter bank analysis, so the speech is a wideband signal. If you pass the wideband signal through a set of band pass filters, for example we have a 16 band pass filters, where if you pass the speech signal through the 16 band pass filters, and we will get a 16 narrowband signals, and then if you try to estimate the energy of these narrowband signals, we will get energy as outcome from every narrowband filter. Since we have a 16 narrowband filters, and here each narrowband will be a bandwidth of about 200 to 300 hertz, so that the 16 filters altogether they can cover a range of around 5 kilohertz or 4 kilohertz. And now if you represent these energy values, whatever the energies that are as outcome of each band pass filter, from filter 1 to filter 16, you have 16 values were there, and all these 16 values if you put together, that can be viewed as a spectral vector. That can be viewed as a spectral vector of size of a dimension 16, because there are 16 components or 16 spectral values for there, and we represent for a particular frame, we represent the spectral vector as a sequence of these 16 values put together, and it is known to be vector, right. So that way we know, we already come across the concept of a vector and all, and whereas the individual component can be viewed as a scalar, but all these scalar values, all these 16 values, outcome values, if you put together, then it forms a vector and all. So now this vector quantization is related to the quantizing the spectral vector, or quantizing the vector on a totality. It is not with the individual values and all. So that is the difference between the scalar quantization and a vector quantization. In case of scalar quantization, each value or each component or of a vector is quantized separately, whereas in case of vector quantization, suppose a vector of dimension 10 means like all these 10 components together as a single, treated as a vector, and this vector will be quantized on the whole altogether. Like each vector will be treated as one entity, and that will be quantized to some reference vector, some the known or nearest or close vector and all. So that way the vector quantization is different from the scalar quantization, and in this topic we will discuss more about the like a vector quantization, how it is different from scalar quantization, what are its advantages, all those things we will try to discuss. So before going to the concept of vector quantization, discussing about quantization or vector quantization, first of all we will see that how do we, what are the different representations of a speech, and for each representation what will be the information rate. It is nothing but for representation of that speech, how many bits are required. Suppose for example, if you want to represent a 1 second of a speech, because after representing you store that speech, right. So therefore for representation of 1 second of a speech, how many bits are required, right. So that way here we now see the different representation of a speech, and one of the known representation of a speech is nothing but like a raw speech, right. So we have that means the speech that is captured by a microphone, it is actually a continuous signal or analog signal, right, and for representing that or for storing that on a machine, we need to digitize that speech, that right. We cannot store the continuous signal, so therefore we had to like represent that, we had to convert that into digital, and then we had to see that how many bits are required and all. So therefore for a raw speech, that means from time domain, and if you want to represent that in the digital one, so first of all we need to sample the signal. So here suppose if we sample the signal by 10 kilohertz, it means that it can able to preserve up to 5 kilohertz, the frequency is up to 5 kilohertz in the speech signal. So if you perform a sampling at a rate of 10 kilohertz, it means that we are representing the speech signal of 1 second using 10,000 samples, So therefore 10 kilohertz sampling frequency is nothing but 10,000 samples per second, and now each sample has some value, right, each sample has some amplitude. So therefore for coding that amplitude, for representing that amplitude value, so we can use 16 bits, right. So here as I mentioned, because each sample has a distinct value, real value, so we cannot represent the real value on a computer because of a finite precision. So therefore here in this context we are representing each sample value with 16 bits. 16 bits means the possible values, reference values will be 2 power 16, right, 2 power 16. So therefore here for each bit, for each sample is represented by 16 bits. So therefore for representing a raw speech, right, we require 160 kbps, that means 160 kilobits per second. That means 1 second of a speech is nothing but 10,000 samples, and each sample for coding for representing we require 16 bits. So therefore it is nothing but 160,000 samples per second, it is nothing but 160 kbps. So this is representing a signal in a time domain, right. And suppose the same signal we can also view that represent in a spectral domain, right. So for representing a speech in a spectral domain, what to do? We have to apply the either Fourier transform, or we have to perform the LP analysis, or we can able to perform the filter bank analysis. So likewise, there are various ways we can able to like convert the signal, time domain signal into frequency domain, right. Suppose for example, if you take an LP analysis for example, then using LP analysis, right, and here for representing the spectral analysis, for a spectral form of representation of a speech, we cannot compute a spectrum for the whole signal, right, because the signal is a time varying signal. So therefore, for computing a spectrum, we need to see that the signal characteristics are steady or stable. So therefore, we need to split the speech signal into frames, right, of 20 milliseconds duration, and we need to shift the frames like at a 10 millisecond shift. It means that for 1 second of a speech, you can able to represent with 100 frames, because the frame duration may be 20 milliseconds, but there is a overlap, right. That means the first frame and second frame, they are overlapped by 50%. Likewise, each consecutive frames are overlapped by 50%. So therefore, for every 10 millisecond we have a frame. So therefore, there are 100 frames per second, right. And on each frame we will apply either FFT, or we can perform LP analysis, or we can use the filter bank analysis, so that each frame is represented by a certain number of coefficients. Suppose for example, if you apply FFT, right, with some appropriate window, right. So therefore, you have the, like for example, for every frame based on the window size of n, we have several values, n values, and then those n values will try to divide that into the like bins, the number of bins as per our requirement, right. So that way each frame of a speech can be represented by a certain number of coefficients, and those coefficients refers to the spectral energies and all if you perform a spectral analysis. Suppose if you perform the LP analysis, then each frame is represented by some linear prediction coefficients, right. It may be that depending upon the order. If it is a p equals to 10, then there will be 10 coefficients. If a p equals to 15, then there are 15 coefficients likewise. So here for the case of generality, we are assuming that each spectral vector is represented by 10 coefficients. That means every frame, for every speech frame we will compute a spectrum. So that spectrum is represented by a spectral vector. It is nothing but represented with the 10 coefficients. Like in case of filter bank, we have the 10 filters, 10 band pass filters. So the outcome of each will be one coefficient. So therefore, all these 10 coefficients put together forms a spectral vector. Likewise, in case of linear prediction analysis, suppose we choose the order p equals to 10. So we will estimate the 10 LP coefficients, right, and so those 10 LP coefficients forms the spectral vector. The same way for in FFT analysis also. So that way each speech frame is represented by one spectral vector with the 10 coefficients. And again for coding that, for coding 1 second of a speech, so it is splitted into 100 frames, right, and each frame has 10 coefficients. It's nothing but one spectral vector, and each coefficient will be coded by 16 bits. So therefore, altogether in case of spectral representation, the speech signal of 1 second is represented by like 16,000 bits per second or 16 kilobits per second. So now if you look at from raw speech representation to the spectral representation of a speech, right, you can able to see the bit rate or the data that is required for storing the speech, like can be like reduced by 10 times, like 160 kilobits per second to 16 kilobits per second. And here please note that this in case of 160 kilobits per second, we will store the speech signal as it is, all samples, everything. But here in case of a spectral representation, we can see that we are going to the transform domain, and then we are doing some approximation, and we are representing the spectral coefficients, and these spectral coefficients are usually in a complex form, but will represent only the real part of the spectral representation. So that way we have in a spectral representation the data rate of 16 kilobits per second are used to represent only the magnitude part of the spectral coefficients. The phase information we are not looking to it as of now. So therefore, recovery of a speech signal from the spectral coefficients will be like in the case of recovery aspects where the spectral coefficients may not be good, because we are not bothered about phase component. So that means without phase component, again the recovering of a speech will be like you may not get back the original speech as it is, but it will be used. The spectral coefficients can be used as feature vectors, and it can be used for different speech tasks. right. So, that way from raw speech to, that means time domain representation of a speech, to the spectral representation of a speech, where you can able to see an advantage of 10 times like lower bit rates are required for representation and all. And now, if you look at the principle of based on vector quantization, like first of all, we are, before going to that, here we will see, because we know that, suppose assuming that the signal we are representing is the speech. Suppose if we know that the information rate in the context of a speech, it means that the signal we are representing is, if it is a speech signal, then we know that the signal contains the basic sounds, because the speech signal is nothing but always it will be associated with a language spoken by a human. So, therefore, it is always associated with it always contains some message, it is in the form of sound units, basic sound units. And we know that for any language, the number of basic sound units will be approximately like around 40, like around like we can say 30 to 50, around 40 is a reasonable number, like approximately around 40 sound units, right. And based on this assumption, because whatever the spectral representation we are doing, spectral vectors, all these spectral vectors are representatives of one of the sound units out of 40, because the speech is the speech signal contains the basic sounds, and the number of basic sounds of any language will be approximately around 40, right. They may vary, but the number, the unique sound units will be around 40, like plus or minus 5, right, around 40. So, therefore, with this representation, if you really want to see, like, and again whatever the spectral vector it may be, it is one of these, it is a representative of one of the sound units. So, therefore, if you represent the spectral vector as it is with respect to the basic sounds, and we know that the number of basic sounds will be around 40, right. So, for representing the basic sounds, like, because there are 40 distinct sounds, so they can be represented by with 5 to 6 bits, with 5 to 6 bits. Suppose if we consider the representation of sound unit will be 5, the number of sound units will be limited to 32 maximum, and if the number of sound units will be more, like 40 or plus, then you can able to use one more bit, so 6 bits. So, with that, the number of distinct sounds that can be represented will be 2 power 6, it is nothing but 64. So, therefore, either 5 to 6 bits can be sufficient to represent each sound unit, and we know that in a speech signal, each spectral vector corresponds to one of the sound units. So, therefore, each sound unit can be each spectral vector can be represented by one of the sound units, So, the sound unit can be represented by either 5 to 6 bits, and we know that the speech signal can be viewed as can be splitted into 100 frames, right, 100 frames. So, therefore, 100 spectral vectors per second, right, and each spectral vector is represented by 5 to 6 bits. So, with that approximation, with that representation, we can able to represent the speech signal of 1 second with 500 to 600 bits, right, with 500 to 600 bits, because we know that it is a speech signal, therefore, it contains the basic sounds, and if our goal is to like analyzing the sounds and discrimination of a sounds and getting a message out of it, if that is the goal of a speech signal, so in that case we know that the basic sounds will be, distinct sounds will be around 30 to 40. So, they can be represented by using either 5 to 6 bits, right. Each spectral vector represents one of the sounds. So, therefore, each spectral vector, the total together can be coded with 5 to 6 bits, 5 to 6 bits. So, we have about 100 spectral vectors per second, right. So, therefore, the total number of bits that are required for representation of 1 second of a speech will be, it is almost like 500 to 600 bits, 500 to 600 bits. And now, if you look at the representation of a speech using a raw speech signal in the time domain, the number of bits that are required will be like 160 kbps, whereas here if you look at here, by using the knowledge of a speech and using quantizing the entire spectral vector, right. So, with that, if you look at the number of bits that are required will be half kbps, right, the 0.5 kbps, right. You can see how much reduction you can able to observe, almost like 300 400 times reduction, because it is about 160 kbps, here it is about half kbps, right. And even from a spectral representation to here also, it is reduced by like 30 times or 40 times reduction, right. But the one thing here is that, as we know that the speech signal is represented by like sound units, but these sound units has a variability. These sound units has a variability because each sound units, based on its context, the characteristics will change. The characteristics will change. That's known to be co-articulation. Based on the preceding sounds and the following sounds, the characteristics of a sound unit depends upon its context. That's known to be co-articulation. And likewise, when you are uttering, the sound characteristics also depends upon the speaker based on his vocal tract shape and dimensions of a vocal tract. And it also depends upon excitation also. And from speaker to speaker, the excitation varies. That means the vocal folds variation, vocal folds vibration, or the frequency of vocal folds vibration, nothing but pitch varies, and it varies based on the gender, and it varies based on the age of the speaker, right? And also, like for example, if you have a speech signal, if you record it in a very quiet environment, the characteristics of the sound units are different, very different from if you record the speech in a open breeze or in an open space where there is a wind blow will be there, and then if you try to record, the characteristics of a sound units will be like a mixture of where our acoustic signal and then with the background also. That means there is a wind breeze, or suppose if you are in a car, for example, there will be car noise. So, and if you are in a train, there is a train noise. If you are in some crowded places where you have like the speech signals of even other speakers' speech also will be interfere with that. So, what I want to convey here is that the sound units, they are unique, but the characteristics of sound units will be vary a lot. So, therefore, instead of representing each sound unit like with a fixed spectral vector, to accommodate the variation, suppose if you accommodate, like for example, for every sound unit, if you accommodate some 25 variations, for example, if you accommodate around 25 variations, right? So, that means based on the inherent variability of a speech, suppose if you can able to represent each sound unit with the 25 variations. Actual sound unit is only one, but the sound unit has a variability as I mentioned, like based on like because of the speaker variability, because of the speaker variability, because of the vocal tract dimensions, because of the gender, because of the age, right, and because of the environment, background environment. So, there are several factors that influence on that. So, therefore, there will be inherent variability of a speech. Not only that, even the same speaker, if you utter the sound in a differently, like in a different times, you do not find the sound, the characteristics of sound units are exactly similar. There will be some, like the inherent variability will be there, right? And not only that, as I mentioned, that the sound unit characteristics also depends on the context where it is there. That means what are the preceding sounds, what are the following sounds, known to be co-articulation. Even that also impacts the variability of a sound unit. So, therefore, here for representation of a speech, each sound unit, if you can able to represent with some by accommodating 25 variations approximately, that means there is no hard and fast rule of 25. Here I just gave the 25 variations, so that if for each sound unit, so that there are 40 sounds, so therefore 40 into 25 will become 1000. So, for that reason I just mentioned here as a 25. Otherwise, depending upon your requirement, you can have more number of variations also can be accommodated. So, suppose assuming that for accommodating the variability, so for each sound unit, if you allow some 25 variations, right. So, with that, like as a spectral vector represent a sound unit, so by considering the variability of a sound unit, the total number of distinct spectral vectors required will be 40 into 25, because 40 are the distinct sounds. For each sound we are accommodating 25 variabilities or 25 variations of it. So, therefore, the total number of distinct spectral vectors can be 1000 approximately, right. Since there are 1000 distinct spectral vectors, we can able to code them using 10 bits, because why? These 1000 distinct spectral vectors are there. So, the 2 power 10, so the 10 bits are good enough, sufficient to represent each of these distinct 1000 vectors and all, each of these distinct 1000 vectors. So, therefore, using a principle of vector quantization, 1 second of a speech, right, it is represented by 1000 frames, 100 frames, and each frame is represented by one spectral vector. So, therefore, there are 100 frames for 1 second of a speech, and that it means that for each frame one spectral vector. So, therefore, 100 frames constitutes to 100 spectral vectors, and we know that each spectral vector needs 10 bits for its representation, right. Each spectral vector needs 10 bits, because we know that altogether there are only, we need to represent whatever the spectral vector will be, we need to represent only with a set of 1000 spectral vectors. How do we got these 1000 spectral vectors? We know that there are only 40 sounds in a language, in a speech of a particular language, and each sound unit is represented by some 20-25 variations of the spectral vectors. So, that way we got about 1000 spectral vectors, and for representing 1000 spectral vector, because there are 1000 unique vectors, and for those 1000 unique vectors, each of them can be represented by 10 bits. So, that way the 10 bits per spectral vector we have arrived here, and with that if you compute 1 second of a speech can be represented by 1000 bits per second, or nothing but 1 kbps, right. So, you can see using a vector quantization you can able to represent 1 second of a speech with 1 kbps, right. And if you look at the previous way of representations, like in case of raw speech you require 1000 samples, right, 10,000 samples, and each sample will be 16 bits. So, that way you it requires about 160,000 bits per second or 160 kbps. If you represent, and the other way is that if you represent the speech using spectral way, and where there are 100 frames, and each frame is represented by 10 coefficients, it means one spectral vector, but it is a 10 coefficients, kinds of 10 values. So, each coefficient is represented by 16 bits, right. So, with that we can see that in a spectral representation of a speech, the number of bits that are required will be 16,000 bits per second or 16 kbps. And here you see in the case of spectral representation of a speech, we are performing a scalar quantization, because here each vector contains 10 coefficients, each coefficient we are quantizing, we are representing with a 16 bits, right. So, because of that you can see that the number of bits that are required will be 16 kbps, whereas in case of vector quantization, see each vector, there are 100 vectors, each vector is represented by 10 bits. So, that is the reason that you see you can able to represent a speech with only 1 kbps. So, therefore, with the vector quantization where 100 frames, 100 spectral vectors, each spectral vector is represented by 10 bits. So, that leads to 1 kbps, right. So, that way you can, by using a concept of vector quantization, we can able to represent the speech in very compact way, and here these 1000 spectral vectors is nothing but which are representatives of the speech vectors, which are representatives of the speech vectors, or which are the references of the speech vectors. That means, whatever the speech vector, spectral vector will be, it will be represented by one of these 1000 spectral vectors, This is very similar to the one where, for example, in case of analog signal where your sample amplitudes are varying from plus 10 volts to minus 10 volts, right. Suppose if you take a real amplitude, there are infinite possible real amplitudes may present in between plus 10 volts to minus 10 volts, but you cannot accommodate, we cannot represent that. So, that is the reason that this plus 10 volts to minus 10 volts, they are splitted into, for example, maybe 20 levels or 30 levels, for example, or 32 levels, for example, right. It means, like, for example, each will be like a 0.5 volt or like 0.3 volt, something like that. So, now what you can do is that actually, so if a particular sample has certain voltage, right, for example 1.375, for example. So, this 1.375 will be approximately represented by something like 1.3 volts, right, 1. So, likewise the actual amplitude will be 1.375, but that is actually represented by 1.3 volts, like, because here in the finite representation the number of voltage levels or number of voltages that can be represented will be only 30, like, even though the signal have plus 10 to minus 10 volts, right, the real amplitude will be, the real voltage will be 1.375, but in the approximation, in the representation with the finite levels, the actual voltage will be represented by 1.3 volts. So, in this process we end up with some error like with 1.375 minus 1.3, whatever is there, like 0.075 volts. That will be the error that will be occurred in this approximation. It is known to be quantization error. Similarly, in the case of vector quantization also the same thing. So, we have infinite possible spectral vectors are available or possible in the representation, but all those infinite spectral vectors are represented by the some 1000 reference vectors. So, these 1000 reference vectors are representatives of all the spectral vectors whatever they are existing and all. So, in the process of this approximation representation, we bound to some errors, we bound to error because the actual vector has certain values, coefficient values, but those are represented by some nearest available code vector or available that particular reference vector. So, in the process that leads to some error and all, and that again that error is known to be the quantization error in this context. And here these 1000 vectors are known to be like all together, the 1000 vectors put together known to be code book. These 1000 vectors put together known to be code book, and each of the individual entries of this code book, each of these 1000 vector is known to be code word, because here I am just introducing a new terminology with respect to the vector quantization. In a vector quantization, the number of reference, all reference vectors, all these like distinct reference vectors, all these things put together known to be code book. And the entries of a code book are nothing but each of these 1000 vectors, and these vectors are known to be, these 1000 representative vectors are known to be code words, right. There is a code book which contains which represents all these 1000, and each of these entry of a code book is known to be code word. And now in the vector quantization, what we do is that whatever the spectral vector is there, this spectral vector is approximated or is represented with one of the code words of a code book. Because here in this context the code book contains the 1000 entries, and now what we will do is that we will take a spectral vector, whatever the spectral vector that is obtained from a speech signal. So, that will be checked with these 1000 code book entries, and whichever the code book entry is having the least distance with this given vector, and the given vector is approximated with that particular entry or with that particular code word. So, in this process there will be some error will be resultant, and that error is not be quantization error. Okay. Yeah, now by using this vector quantization, we will look at what are the advantages and what are the disadvantages also. So, the advantages are very clear. You can see that one advantage is that reduced storage. That means we can able to represent the speech in a very compact way, not only speech, for any signal also we can represent in a very compact manner. So, therefore, the storage that is required for representing the speech, for storing that information, we require very less storage. So, therefore, reduced storage is nothing but compact representation. Those are the advantages. And the other one is the reduced computation when determining the similarity. Because here we are representing the entire spectral vectors using 1000 entries, right. And suppose, for example, when if you want to perform a task for some speech related task, we know that the entire spectral vector, all the spectral vectors are represented by code book of 1000 entries, and for a given task we need to compare only with these 1000 entries. The computation cost will be reduced. Whereas earlier you can see that we have like a lot of spectral vectors are there. If we want to find out any similarity match and all, so we need to check with like all the possible vectors and all. So, they are very huge in number. So, therefore, the computational cost is very high. Whereas here the computational cost is very much limited, because we have altogether whatever the code book size dictates, like we need to check with only the code book size only with the entries that are there in the code book. So, therefore, the computational cost will be reduced. That means we need to check the similarity of a given vector only with these 1000 vectors. So, with that we can come to know about like which code book entry is close to this one, then it will be approximated with that, it will be represented with that particular code book entry, right. So that way the computation cost will be very much reduced to find out the similarity, determining the similarity, right. And the third one is that actually by using this vector quantization, you can able to, it's a kind of, the signal can be represented in a discrete way with the sound units, with approximate labels, because we know that each sound unit is represented by, because here in this context of vector quantization, as we know that since it is a speech, it contains different sound units, altogether the number of sounds will be like around 40. So therefore, with that knowledge, here this sequence of spectral vectors can be approximated to like with the sound labels, with the labels of sound units. It means we can able to represent the signal in a discrete way with the labels of sound units. So that is the advantage in the context of a speech recognition point of view. Then coming to the disadvantages of vector quantization will be like obvious, because here there is inherent spectral distortion in representing the actual spectral vector. That is true, because we have actual spectral vector will be there, but that will be, we are representing with its approximation, right, because whatever the spectral vector will be, it will be represented with only with one among the 1000 vectors. So that leads to some spectral distortion, that is spectral is known to be some error in the representation and all. And the second one will be the storage required for a code book vectors that depends upon the code book size. Here you can see the spectral distortion that depends upon the code book size, because if there are more number of, if the code book size is very large, right, then the error will be reduced, because as you see that each sound unit will be represented by certain number of variations. Here in this context we represented with, we accommodated with 25 variations. Suppose if you accommodate the more number of variations, right, then the approximation will be like more accurate. That means the given spectral vector can be represented with a less quantization error. So if you want to minimize the quantization error, it means that we need to accommodate the more variations in the spectral vectors. If you want to accommodate more variations in the spectral vectors, means then with that the code book size will increase. If the code book size increase, then again its effect will be on the storage. That means the storage that is required will be more if the code book size is increased. And not only that, again the complexity also, the similarity analysis complexity also will be increased. So therefore there will be certain the trade-offs, so that will be possible that exists in the vector quantization. So the trade-offs here will be, you can say, one is the quantization error, and second one is the similarity computation, and the third one is the storage. So these three are like, suppose if you want to minimize the quantization error, then what happens, then the code book size will increase. If the code book size increase, then these two factors will affect. That means the similarity computation complexity will be increased, because suppose the code book size equals to 1000, we need to perform only 1000 comparisons for representing a spectral vector with the code book entry. Suppose if you make the code book size will be like, for example, 10,000 entries, then you see that the number of comparisons will be 10,000 for every spectral vector, right. And not only that, along with the computational complexity, rise in computational complexity, and the storage requirement also will be increased, because earlier the code book is represented by 1000 entries, and now the code book is represented by 10,000 entries, right. So therefore there are the trade-offs. So we need to strike a balance between the code book size versus the quantization error and all, right. So these are the, like when you try to analyze the vector quantization, there are certain advantages, disadvantages, and we need to see that we need to balance these like the code book size versus the quantization error and all. Then coming to the like the implementation of vector quantization, that means here we see that in the case of vector quantization, what we are doing here, we have like each sound unit has like a tremendous variability will be there, as I mentioned that, So that variability is due to the speaker variability, and then even the speaker also, within the speaker also there is a variability because of the context, because there are only 40 sound units and all, and if you try to look at the vocabulary of the speech, a vocabulary of a particular language, each language may have lakhs of words. That means there are several possible combinations of sound units that leads to a different words. And as I mentioned, that each sound unit, the characteristics of the sound unit, that depends upon its context. Like it means that whether the sound unit is present at the beginning of a word, end of a word, and that means the positional information is also important, and as well that depends upon what is the preceding sound, what is the following sound. So there are various possibilities will be there, and for all these possibilities there will be certain variations are there, right? And not only that, if the speech that was captured in a different environments, and we have and again this noise or this environment also will influence the characteristics of sound units. So all together, like there are different variabilities that exist in the speech sounds, and to accommodate that variabilities, that means there are what I mean to say is that in the when you are representing, when you are deriving the spectral vectors basically there are varieties of there is a lot of variability that exists in the spectral vector representation, but as we know that all these spectral vectors, they represent some 40 basic sounds, so therefore with that what we are saying is that there are 40 basic sounds, and then to accommodate the variability, for every basic sound we are representing every basic sound, or we are accommodating some variations of that sound, at a very gross level. So that way earlier we have seen that for every sound unit we are accommodating around 25 variations. So that way our code book size has been reached to 1000. So therefore here what we need to do is that we need to prepare a code book, or we need to design, or we need to develop a code book. How do we develop a code book? It means that how do we prepare a code book with 1000 entries? It means that for 40 sounds, each sound will be around 25 variations. So what we need to do is that somehow from the training data, that means the training data will be like having the varieties of speech, like the speech will be spoken by different speakers, different genders, different age groups, and speech will be collected from different environments, different devices, and so on. So that gives you the varieties of a speech. So we will collect all the speech, and from that we derive a feature vectors, and from that feature vectors somehow, that depending upon the code book size, we need to cluster those feature vectors. We need to perform some clustering, or we need to split the entire the whole set of spectral vectors, right, into different groups, into different clusters, different groups, right. We need to split that into different groups, right. So for splitting that into different groups, we use some clustering algorithm. So with this clustering algorithm, automatically given, suppose for example you have some 10 hours of a speech is collected by using different varieties of environments, varieties of speakers, and so on. So we have about 10 hours of a speech. From the 10 hours of a speech, we will get some lakhs and millions of vectors, and from these millions of vectors, so we need to pick up some 1000 representative vectors that forms a code book. So how to pick up those 1000 vectors? So for that what we need to do is that actually here we will cluster these 1 million or 10 millions or like 1 billion spectral vectors into 1000 clusters or 1000 groups. We have to split that into 1000 groups, where each group represent the like a cluster or like some like a variation of one of the sound units and or something like that. So that way we will cluster the training data into like the desired number of groups, clusters, right. Maybe suppose your code book size equals to 1000, then you split this 1 billion vectors into 1000 groups, and then from each group we will pick up one vector, one representative vector. How do we do that? So after splitting that, after you cluster that, each cluster you compute the centroid. So those centroids of these clusters, they can be formed as a code book, they can be formed as entries of a code book, or they can be formed as a code words of a code book, right. So that way a code book can be formed. So that way the code book is developed. So once the code book has been developed, it is nothing but now we have a code book, that is we have 1000 representations or 1000 representative spectral vectors. Now from an input speech, if you want to derive any features or whatever, from input speech we derive a spectral vector, and these spectral vector now we are given to the quantizer. Quantizer is nothing but whatever the code book is there, we will compare the given spectral vector with each of these code book entry. Like, and it's nothing, this here compare is nothing but just computing the similarity or distance between the given spectral vector to each of the code word of a vector quantizer. Then we will get a different distances, and among all those distances, whichever gives the minimum distance, then that particular code word index will be transmitted, or the particular code word index will be given as a code or is a representation for the given spectral vector and all. So this is a gross philosophy of a vector quantization in the context of speech. So the basic elements of this vector quantization will be, one thing is that we need to have a training data is required, right. So the training data is nothing but a lot varieties of a speech that is collected from different aspects, like different speakers has to be involved, different age groups have to be involved, right, and different emotions have to be involved into it, and different accents has to be involved, and different environments has to be considered, and different languages, and then different devices to be, that means speech collected through microphone, then speech collected to like laptop, and the speech collected to your mobile phone, speech collected through the telephonic channels. Likewise, from varieties of speech has to be collected, that is a training data. Like, then from the training data somehow you need to derive 1000 representative vector, that means we need to develop a code book. So for that, by using the clustering methods or clustering algorithms, we will split the speech, the entire speech into some 1000 clusters, right, and from each cluster we will pick up as one of the representative vectors. So that is nothing but whatever the cluster is there, from that cluster we will compute a centroid of a cluster, and that centroid happens to be your code word corresponds to that particular cluster. So we have 1000 clusters, so therefore from each cluster we will compute a centroid, and that centroid vector whatever is there, that becomes a code book entry or a code word. So that way we will form a code book, right. Then the next one is the comparison, right. Once the code book is ready, code book has been developed, then afterwards the task of the code book, or the purpose of this is nothing but, so we need to represent the speech. So take a, suppose if I record a speech, you have a lot of speech is there, and for representation of that or for storing that, one way is that using a vector quantization you can store that, right. So that way whatever the speech, from that we will derive the spectral vectors, and that spectral vector is represented by the index of a code book. How do you do that? This spectral vector is given to the is compared with the entries of a code book in a quantizer. The quantizer block is nothing but, the purpose is nothing but it performs a similarity match and deriving index as outcome, right. It means the quantizer, you can see there are two inputs, one is the code book and the other one is the spectral vector derived from a speech. So these are the two inputs. So the spectral vector, their code book means there are 1000 entries, that means there are 1000 representative spectral vectors are here, and here there is a one spectral vector which need to be coded, and this spectral vector is compared with each of this entry. So when you compare with each of the entry, you will get a distance, that means the distance between the spectral vector with the first entry of a code book. You will get maybe the distance between the first entry of a code book with this spectral vector. Likewise the second entry, third entry, likewise all the 1000 entries will get 1000 distances you will get, and from these 1000 distances we will see that what is the minimum, where is the minimum distance and all. So whichever the code word offers the minimum distance, now that code word we will see the location of the code word. So based on the location of a code word, we will represent that with the the appropriate code. That means whatever the index is there, suppose the code word is 523, then that 523 index, that is nothing but representation of this particular spectral vector. So that way you can able to represent the input speech with the indices of the vector quantization code book and all. So this is one way of representation of the spectral vectors and all. And now this representation, right, can be used as a feature vector for performing various speech tasks, right. So that means whatever the code book indices are there, so that forms again the representation of a speech, and that can be used for varieties of speech tasks, right. The way they are, how they are, and also based on that this can be used for, like for example, if you want to retrieve the information for from a speech, like from a speech corpora, that means you have a lot of speech data was there, and suppose if you represent the speech data by using these code book indices, then the entire speech data is represented using a sequence of these indices and all. Then suppose if I want some speech data to be retrieved, for example, then I will give a query. So this query also will be represented in the form of this code book, and these code book indices will be the sequence of these code book indices of the query will be matched with the speech query, and whenever there is a possible match and all, then that particular corresponding speech segments will be retrieved as output. So that way you can use the vector quantization for varieties of applications and all. So we will stop here. In the next class we will continue this vector quantization. Okay, thank you.